Good morning, students. I welcome you all for this session. So, in the previous sessions, we have considered analysis of singly reinforced beam. Then we have completed analysis of doubly reinforced beam. Let us move on to the next beam, that is how to analyze the flanged beams. Okay, that is analysis of flanged beams. So, flanged beams are nothing but T beams and L beams. So, what is the difference between this rectangular beam and this T beam and L beam? Okay, so normally if you consider in all structures, okay, so whatever we are going to construct, okay, buildings, so most of the cases, right, so we use these T beams and L beams. So why these are called as T beams or L beams? So what is the difference between this rectangular and this beam we are going to see. So in actual practice, T sections and L sections are more common, okay, than the rectangular sections. So we are providing in almost all the cases T beams and L beams. Okay. So what is the specialty of this T beams? So here, if you see this sketch, okay, so these are the beams. Okay, over these beams, a slab will be there. So what we are going to do when we are putting the concrete, right? Simultaneously, this slab and beam are casted. Okay, we'll put the concrete, right, for both the elements. Okay, so the casting will be done simultaneously for slabs as well as beams. Okay, that's why these two elements will going to act as a single unit. Okay, so since we are casting simultaneously, so the behavior will be as a single unit, and this will going to be considered as a T section. Just observe this. This is a slab, okay, and this is the beam. So over this beam, the slab will be casted simultaneously, and some part of the slab on either side of this beam will be considered. So whatever you are seeing, this is the width of the slab we are going to consider for the design. So this shape, what we are seeing, this shape is like a T section. Okay, that's why this is called as T beam. So this complete portion now, slab and this beam will be casted simultaneously, and they will going to act as a single unit. So that's why we are calling this as T beams. And if you see the end beams, the slab ends here. Okay, the slab will going to end here, and this is the beam. Okay, and see this shape, this will be like a L. So this is L beam, this also L beam. So normally the end beams, okay, where the slab ends are considered as L beams, and the intermediate beams are considered as T beams. So remember, T beams are nothing but the beams in which slab and the beam are casted simultaneously, and they will going to act as a single unit. Okay, then see the diagram. Then what are the elements of this T beam? Now see, this is the section we can see here. So these are end beams are L beams. This is a T beam. Okay, now if you see, this BF is called width of flange. Now what are the elements of this T beam? So the elements of T beam are this slab, whatever you are seeing, this portion is considered as flange. This is called as flange, and this beam is called as web or rib. Okay, so the elements of T beam are, okay, so one is this BF, that is flange, this will be flange, this will be web or rib. Okay, these two are the important elements of T beam. So this width of flange is considered as BF, and depth of slab, what you are seeing, this is DF. F indicates flange. This portion is flange. Okay, so this is width of flange, that is BF, depth of flange DF, then this is web, then this will be width of web or rib, that is BW. Okay, so that's why here it is shown. This is width of flange, okay, depth of flange, width of web or rib. Okay, then this is depth of flange. Then now what are the advantages of this T beam compared to the rectangular beam. So why you have to go for this T beams instead of a rectangular beam? See, these are the three major advantages of T beams. Okay, so since as in T beam, beam and slab are casted simultaneously, means we are going to put the concrete simultaneously in beam as well as in slab. So beam and slab are casted simultaneously, hence casting can be done at the same time, therefore saving in cost of construction. So construction cost will be reduced because at the same time the beam and slab are casted simultaneously. So we can reduce we can save the cost of construction. Then second advantage, slab and beam combined together. So they will going to act as a single, no? So when you are casting simultaneously, they will going to behave as a single beam. So slab and beam combined together, they will going to carry more bending moment. This is important. Compared to the rectangular beam, what we have seen in the singly reinforced and doubly reinforced beam. So compared to the rectangular beam, if you provide T beam, they will going to carry more bending moment. Okay. For the same section, these will going to carry more bending moment. That is the second advantage of T beam. Then third advantage, for same sections, okay, for same sections, T beams have more moment of resistance. That is, if you compare strength wise also, they will going to give more strength. Okay, T beams will be giving more strength compared to the rectangular beams. So there are three advantages. One advantage is we can save the cost of construction. Second, okay, since slab and beam combined together, they will going to take more bending moment. Third, flexural strength of T beams, okay, or moment of resistance of T beam will be more than the rectangular beams. So that's why we are preferring T beams and L beams. Okay. So now the next important thing is how to calculate moment of resistance of T beam or flexural strength. Okay, what will be the strength of the T beam? That is moment of resistance of T beam. So there are basically three cases we are going to consider. So the first case, let us concentrate on case 1. Okay, what is case 1? Again, we will consider the neutral axis. Neutral axis lies within the flange. Okay, neutral axis, the case 1 is neutral axis lies within the flange. Flange means this portion. Okay, this is the flange. Whatever you are seeing, this slab is nothing but flange. Okay, so what is the first case? We assume that neutral axis lies within the flange. Means, now see, if you see the diagram, this is the flange or this is the slab and this is the beam. They will going to cast simultaneously. So this will going to act as a T beam. And as usual, this is width of the flange, that is BF. B means width, F means flange, BF means width of flange. Okay, DF, depth of flange. Okay, then this is width of web, this portion beam. Whatever you are seeing, this is beam. This beam is considered as either web or rib, RIB, web or rib. So this is width of beam, or that is denoted as BW. BW means width of web, or BR also. In some notations you can see BR also, that is width of rib. Okay, and here for this beam EST will be provided. Okay, now from the top of the flange, okay, from the top of the flange to the center of reinforcement, it is effective depth of the T beam. Effective depth, that is small d of the T beam. And this portion, what you are seeing, this is DW, that is depth of web. This portion is web. So from here to center of reinforcement, this is depth of web. Okay. Now see, this is DF, depth of flange or depth of slab. Now let us assume first case what? XU is less than or equal to DF. So XU is what? Neutral axis from the top. Let us assume that neutral axis will be within this flange. It is not outside the flange. Okay, it is XU less than or equal to DF. So this is XU, this is DF. So XU is less than DF. Okay, XU is less than or equal to DF. Okay, now there will be two zones now. Whatever you are seeing this dotted lines, okay, this hatched portion is the compression zone. Okay, this is the compression. So above neutral axis, okay, this above neutral axis, this is the compression zone. Okay, here also concrete is there, but it is neglected. Only we are going to consider this part. Okay, above this neutral axis is compression zone and this is tension zone. Okay, there will be two zones now. This is compression zone, this is tension zone. So shown here. Now see, only I have shown above this neutral axis. This is XU now. Okay, up to neutral axis, this is XU, this is BF, breadth of flange. Okay, then this is AST. So only two zones. This is compression zone, this is tension zone. Okay, now let us consider BF. What is BF? Width of or breadth of flange. What is DF? DF will be depth of flange or depth of slab. Then BW, width of flange or width of rib. Okay. Now what are the steps to be followed? The first step, how to calculate this moment of resistance now. So the first step is, as usual, you have to calculate the depth of neutral axis, assuming neutral axis lies within the flange. Let us assume, okay, let us assume that this neutral axis is inside the flange. Okay, means XU is less than DF. XU is less than or equal to DF. This portion. Okay, first step. So you have to calculate the depth of neutral axis. That is, you have to calculate XU now. Okay, what is the depth of neutral axis? XU will going to calculate. So now, equating total compressive force is equal to total tensile force. Equate C is equal to T. Now what is C now? Total force. This is the compression zone. What is the total force in this? What do you mean by force? Force is equal to stress into area. This is concrete now. So force is equal to what? Stress into area. Okay. Now see, force is equal to stress into area. Again, tensile force is equal to stress into area. So this is C, this is T. Force means stress into area. Again, this tensile force, stress into area. Then what is stress? What is stress in this compression zone? Stress is 0.36 FCK. Okay, stress is 0.36 FCK. Already we know this. This is stress and area. What is the area of this portion now? What is the area? Width is BF, depth is XU. Only we are considering this part. This part. What is the area? BF into XU. So stress is 0.36 FCK. This is stress. Area is BF into XU. Similarly, tension zone. This tension zone. So here it is concrete is there. It is neglected. So only steel will going to take the tension. So what is the stress? Stress is 0.87 Fy now. Steel 0.87 Fy. Area is AST. Now see here. Okay. Stress is 0.87 Fy. This is stress and area is AST. Okay. So total C is equal to total T. Okay. Total compressive force in concrete is equal to total tensile force in steel. So this is stress into area, that is 0.36 FCK BF into XU, then 0.87 Fy into AST. Only change if you compare this with the singly reinforced beam or doubly reinforced beam. Singly reinforced beam. In place of B, we are substituting BF. Other than this, all are same. So wherever B is there, we can substitute BF. Now because this is width of the beam now. Okay, BF. So what we want? We want neutral axis depth XU. So XU is equal to 0.87 Fy EST divided by 0.36 FCK BF. Okay, this. So this will going to give XU. Okay, from this we can calculate the neutral axis depth from the top, this XU. Now what we have assumed? We have assumed XU less than or equal to DF. Now compare. DF will be given in the problem, that is depth of slab will be there. Now what we have assumed? We have assumed XU less than DF. Now you have to check whether XU is less than DF. So calculate XU from this equation and compare XU and DF. If XU less than DF, okay, if XU less than DF, then our assumption is correct. Initially we have assumed this XU less than DF. So after calculating this XU, compare this XU and DF. If XU is less than DF, our assumption is correct. Okay, then go to the second step. Okay, if XU is not less than DF, so we cannot go for this second step. Okay, our assumption is wrong, then we cannot go for this. Next revision will be there, assumption will be different now. But if XU is less than DF, okay, then go to the second step. So what is second step? Now second step, you have to calculate XU max. Okay, that is maximum depth of neutral axis. This is actual depth of neutral axis. So XU max is maximum depth of neutral axis. We know that XU max upon D is equal to 3 values for depending upon the grade of steel. Okay, Fe 415, Fe 250 and Fe 500. So depending upon the grade, this value will going to change. So from IS 456 2000, you can calculate XU max upon D, then XU max you can calculate. Okay, D will be given in the problem. So XU max is equal to D into that ratio. So once if we get XU max, now compare this XU and this XU max value. Okay, XU and XU max you will going to compare. So comparing XU and XU max. Okay, comparing XU and XU max. Okay, so then again condition, if XU less than XU max. Okay, whatever this XU will going to calculate, if it is less than XU max, then what is your comment? The section is under reinforced T section. So the section is under reinforced T section. Means XU is less than XU max, means it is under reinforced. Anyhow it is a T beam, it is under reinforced T beam. Okay, then now it is confirmed that it is under reinforced. Then calculate moment of resistance. Okay, if it is under reinforced, then same as it is singly reinforced, what we have calculated? Moment of resistance. So fourth step, what is fourth step? Moment of resistance, that is ultimate moment of resistance mu or factored moment mu. So moment mu is equal to, what is moment is equal to? Force into perpendicular distance. Remember, force, moment is equal to force into perpendicular distance. So here perpendicular distance means lever arm. Okay, perpendicular distance means it is lever arm. Okay, so moment is equal to either compressive force C into lever arm or tension force T into lever arm. So from these two, any one you can use if it is under reinforced section. Okay, right. Then mu is equal to first compressive force C into lever arm. Force into perpendicular distance means it is lever arm. So what is compressive force C? C already you have calculated here. Okay, here what is C? 0.36 FCK BF into XU. This is C now. Okay, C 0.36 FCK into BF into XU. So this total is C. Okay, here 0.36 FCK BF into XU. This is total compressive force C into lever arm or perpendicular distance between this to this. This is lever arm. Okay, it is D. Okay, D minus 0.42 XU, lever arm. D minus 0.42 XU. So from this you can get the mu, ultimate moment. Or if you want to use tension force T. So tension force T. So again T is what? Shear. Stress into area, that is 0.87 Fy into AST is total T. So this T 0.87 Fy into AST, this is T into lever arm, this is remains same, that is D minus 0.42 XU. So from this you can get the MU. This is if XU is less than XU max, that is if it is under reinforced section. If XU is greater than XU max, then it is a over reinforced section. Then in place of XU, wherever XU is there, you can put XU max or XU limit. That is the only change you can make. Okay. If it is under reinforced section, okay, either using this equation or this equation, you can calculate MU. If it is a over reinforced section, okay, same you can use this or this, but only change is wherever XU is there, you can put XU max. Okay, so that we can calculate the moment of resistance. So this is case 1. What is case 1? If neutral axis within the flange, means it is inside the slab. Okay, that is XU less than DF. Okay, so next case number 2, if it is outside the flange, we will going to consider in the next class. So I hope you have if you have understood this procedure. Okay, so in the next class we can consider the case 2. Okay, so thank you very much for attending this session. Thank you.